Welcome to Unit 5, Lesson 1, Rational Functions Using Transformations. So when we talk about a rational function, it's a function that can be written in the form of f of x is equal to p of x over q of x, so two functions on top of each other. And p of x and q of x are polynomial expressions where q of x cannot equal 0. So just remember that the bottom of a fraction cannot equal 0 because it's undefined at that point. That gives you a hint where your vertical asymptotes will be. So remember that an asymptote is a line that the graph cannot touch. It will forever approach it, but never actually touch it. Now, when we're graphing these rational functions, p of x over q of x, if they're polynomials with no common factor, there's some steps that you need to do. So they're listed there for you. First, find the y-intercept. That's where x equals 0. So if you were looking at these equations up here, you just plug 0 into wherever there an x is, and it will tell you where the y-intercept is. Find the zeros of the numerator by solving the equation p of x equals 0. So set y equal to 0. Sometimes it will be factored already, and you'll be able to see where exactly the intercept is without doing any math, but if you're not sure, then you can just set y equal to 0. Identify vertical asymptotes and discontinuity points. We'll get to the discontinuity points later in this unit, but the asymptotes is of course wherever it's undefined. And then find and sketch the horizontal asymptote. So there's some rules behind this. You need to look at the degree of the polynomials. If the degree of p of x, that's the top of your fraction, is less than the degree of q of x, then the line y equals 0 is the horizontal asymptote. So you can see here the degree is 1, and here the degree is 2. So at y equals 0, you'll have a horizontal asymptote. If the degree of p of x is equal to the degree of q of x, then the line y equals a over b is the horizontal asymptote. So you find your a value on your biggest exponent factor, and also the a value here, of course it's 1, we don't write it in, but it's 1x, so we have 3 over 1, and you'll have a horizontal asymptote at y equals 3. The last one, if the degree of p of x is greater than the degree of q of x, so here you have x squared over x, then there's no horizontal asymptote. After that, you can find the mapping points. Some good points to start with. You really only need a few, and then you can just draw the general direction of the graph. Some good points to start with are typically x equals +1 and -1, because 1 over 1 doesn't usually change. So it will give you a good mapping point to start with. You need to understand the end behavior. Go back to the first lesson of Unit 4 that showed the different types of graphs and their general shapes. Once you know that, you can see is the polynomial positive or negative, and that will determine your end behavior. And then once you have a few points on your graph, you can just use smooth curves to complete it. There's a couple different ways we can determine the graph of a rational function. The first way is to use a table of values. So if you're given the function 10 over x, use the table of values and a graph, identify the characteristics. So we have some information here, a non-permissible value, it's not allowed to equal 0 because that would make it undefined. The behavior, as x approaches 0, the absolute value of y becomes very large. So if you look at the graph down here, as it gets close to 0, it just kind of shoots off into negative and positive infinity. You can give your domain and range. You could also say that it says it right here, x cannot equal 0 and y cannot equal 0, and then it includes all other values except that 0. The equation of the vertical and horizontal asymptotes is x equals 0 and y equals 0. So this is a positive function. We know that it will show in quadrants 1 and 3. If there was a negative symbol, you'd have it here 2 and 4, but it's not. So you can just pick some x values. You don't need to go to this extent. Most times you'll be given a graph that only goes up to 10 negative and positive. So you can just plug in a few values and find the corresponding y value to do that, and then just plot your graph. You can see here in this example, they've just picked a couple key points and then just drawn the curve in, and that's perfectly fine. The other way we can solve these problems is by using transformations. So this should look like something you've done before. We have this function given y equals 6 over x minus 2 minus 3. The form of this, the general form, is y equals a over x minus h plus k. Now, what those numbers represent have not changed. H is still a horizontal shift, k is still a vertical shift, and a is definitely a stretch. So the vertical asymptote where x equals h exists. There's a horizontal asymptote where y equals k, and knowing where the asymptotes are and tracing them first can help you graph and analyze the function. So once you know those undefined values, then you're able to kind of draw a general form of the graph. So here we have some information about this graph in the table. In your example, it shows step by step kind of what's being drawn. So you start with y equals 1 over x, okay, just a general graph. Then you transform it to y equals 6 over x. So notice how the shape changes. And then after that, of course, you apply your horizontal and vertical shifts. So it's stepwise exactly how we did it at the beginning of the year. All you have to do is just remember what those values of a, h, and k are representing. Once you know that, then you just pick some common points and draw the shape of that graph. We can also graph a rational function with linear expressions in the numerator and the denominator. So you're given this example, y equals 4x minus 5 over x minus 2. Identify any asymptotes and intercepts. I apologize, I didn't leave room for the graph or the work, so it kind of goes like this down the page. So our asymptotes, x cannot equal positive 2, and y cannot equal positive 4. So once you know that, then you can kind of plot your dotted lines onto your graph. I did the work for it over here, as well as finding the x-intercepts. One of them is at 1.25. That's when y equals 0. So we have two different intercepts. We have the x-intercept at 1.25 and 0, and then the y-intercept at 0 and 2.5. And once we've done that, we can rewrite the equation algebraically to get this form. So the answer is this, y equals 3 over x minus 2 plus 4. The work for it is down here on the right-hand side. So we have this original function, and what we're trying to do is change it into that general form at the end. Now, you might be wondering, where the heck did this plus 8 minus 8 come from? Because it kind of appears out of nowhere and it's not something you've really seen before. In this circumstance, what you need to do is look at your bottom term. That tells us we need an x minus 2 on the top of the fraction to be able to cancel out and isolate the variables. So if you have 4 here, 4x, you want to think about what times 4 and minus 2 will give you that second variable. So it becomes 4x minus 8. And then we want this to equal 0. So if you subtract 8 here, you also have to add 8. And you're kind of treating these terms as two separate terms. So 4x minus 8, factor out the 4, take the 4 out. Inside the brackets, you're left with x minus 2. And then 8 minus 5, you're left with positive 3. This is a little bit tricky, but if you practice it, you will get the hang of it. Now on the top and bottom, we're getting closer to what we need to do. You have x minus 2 over x minus 2. Those would definitely cancel, and then you're left with plus 3. Separate these terms, so you'll have 4 times x minus 2 divided by x minus 2. These guys make 1. You're just left with 4, and then 3 over x minus 2. Once you're at this format, you don't have to do any more math. You just need to move the numbers around. So be careful of your signs here. Make sure that the signs go with the thing that you're moving. All we did was switch the positions though, 3 over x minus 2 plus 4, and then it is in that y equals a over x minus h plus k format. Once you have that done, it becomes very simple to graph the function that you're given. There's 2 additional examples here. The first one is here. The work is kind of in that squiggly line. So we have, we're trying to find the equation of the rational function. So first thing we need to do is find the horizontal and vertical asymptotes. You can see this one has an asymptote at y equals 0 and x equals 0. And then we know that the function is in this format because we have those asymptotes. It's going to equal y equals 1 over x. And what we want to do is solve for a to figure out what is our stretch. What you need to do is just find one point on the graph. Any point you choose will work, but try to pick one that goes cleanly through a coordinate. So I picked 2, -2, and filled in that value for y and x. So you have -2 is equal to a times 1 over x, 1 over 2. Of course, if we simplify that, that's a over 2, and then we're just isolating the a. So 2 times -2 gives us -4 equals a, and we will have y is equal to -4 over x. Keep in mind this is equal to y is equal to a times 1 over x, if you're confused about where that -4 came from. Similarly, in the bottom here, we have a vertical asymptote at x equals 1, and we have a horizontal asymptote at y equals 1. So determine your x and y intercepts. We know that x cannot equal 1. And then if you remember, your original graph would be here, right? Going along the x and y axes, and you can see that we've shifted up 1 and shifted left 1 to create this graph. The general shape has not changed of the 1 over x format, but we have that horizontal and vertical shift included. There's no practice questions for this section of the unit, but you can go ahead and complete the lesson 1 homework.